To build resilient applications, we need a way to reliably persist data across sessions. Things like user preferences, authentication tokens, and basic configuration states. Apple provides a standard, out-of-the-box solution for this exact requirement: UserDefaults. Under the hood, UserDefaults operates as a dynamic dictionary. It functions strictly on a key-value storage system. When you want to extract data from the system, you query it by passing in a specific string identifier to find the matching value. This introduces a structural vulnerability. Because the API relies on hard-coded strings, it forces developers into a stringly typed access pattern. Every time you need to read or write a specific value, you have to manually type or copy-paste the exact same string across your codebase. Scattering raw strings like this strips away structural organization. What should be a centralized configuration problem becomes completely distributed. Relying on scattered, plain text strings introduces a consistent risk into an otherwise strictly engineered application. Swift defends against structural vulnerabilities using compile-time type safety. This is a mechanism that verifies data structures before an application ever runs. Strict static typing prevents logic errors outright. If a function expects a Boolean, the compiler simply will not let you pass in an integer. However, user data string keys bypass this protective compile time boundary. The compiler has no ability to verify if a given string key actually matches a corresponding value inside the storage container. Here we have a typo in our string key, isDarkMode. The compiler evaluates only valid syntax, so the code builds, masking the error. At runtime, the app searches for this misspelled key, comes up empty, and fails silently by returning a default false value. These silent runtime failures create bugs that are difficult to track down, especially when strings are spread across dozens of files in a large codebase. We need to bridge this gap by forcing the dynamic, string-based key-value API into a safe, compile-time verified structure. To protect the application, we need to build an abstraction layer that sits between our codebase and the raw UserDefaults API. This layer must be a reusable container capable of handling any data type, Booleans, strings, or integers, without duplicating code. We start by defining a UserDefault struct, declaring it with a generic type parameter. The T syntax allows the struct to adapt to whatever data type the developer eventually specifies when using it. Inside this struct, we need the first essential input, the string key that will actually interact with the database. Second, we need a fallback value to ensure the application always has a valid state, even if the database is empty. The default value utilizes the generic type T. This ensures the fallback matches our intended data type perfectly. Finally, we define the actual storage container where the data lives. Defaulting this container to .standard is practical for most use cases, while still allowing dependency injection for specialized testing environments. At this point, the struct holds all the necessary data, but it is currently a passive data holder. We need an active row that intercepts code execution. To achieve this, we will invoke a specific compiler directive that changes how Swift interacts with the struct. Swift provides a feature designed for this type of architectural abstraction, the property wrapper. We apply the @property_wrapper attribute directly to the top of our newly built struct. This attribute instructs the Swift compiler to utilize this struct as a protective shell around a variable. This attribute requires the struct to implement a specific property called wrapped value, complete with a getter and a setter. The get block intercepts any attempt to read the variable. It routes the request through the user data's object for key logic and returns our default value if the read fails. The set block intercepts any attempt to change the variable, writing the new value to the container using our controlled string key. This hides the raw user data's commands behind a clean interface. By encapsulating the read and write logic inside a property wrapper, we have isolated the fragile string manipulation into a single environment. Now we can transition from building the tool to deploying it within a codebase. First, we establish a dedicated environment for global application states, like a settings struct. Here is the syntax for applying our new property wrapper to a static Boolean property. In this one line, we pass our required inputs directly into the wrapper, the string key, and the safe fallback value. This single line localizes the hard-coded string isDarkMode. Because this string is now written exactly once in the entire project, the risk of a typo breaking the app elsewhere is removed. This contrasts with the legacy method of scattering raw string queries across multiple view controllers and helper classes. Centralization resolves the risk of runtime typos by creating a single verifiable source of truth. From the perspective of a developer working anywhere else in the codebase, the final execution pattern is entirely streamlined. When you assign true to this property, the compiler pushes it through the wrapper into the underlying user data set command. This yields three major advantages. First is type safety. The compiler now strictly guarantees that isDarkMode will only ever accept or return a Boolean. Second is readability. Calling settings.isDarkMode equals true feels like interacting with a native Swift property, obscuring the database interactions underneath. Third is reusability. With a generic parameter, you can apply this exact pattern to integers, strings, or data objects without writing new logic. By leveraging property wrappers and generics, engineers replace manual key value lookups with compile-time verified APIs.